Okay, this video is for AP Calculus, specifically BC. Um, this topic is another way to do volumes of solids in revolution called shell method that works in some cases where it's impossible to use disk method. There are also some problems which are easier to do with shell than disk. Like you might have a problem which would be a washer and require two integrals for disk method, but you can do it with a single integral shell. Um, all the problems that are on the AP Calculus BC exam and the AB exam, they can be done using just disk method. So this is not required for the AP test, at least we've never seen one that's shell. But it is officially part of the course for college courses and for Rio Salado, so we do include it. And I think it's good to know as an alternate method. So let's take a look. We'll start by looking at a problem which we would not be able to solve with disk. So let's say we wanted to find the volume of the solid obtained by rotating this curve, y equals 2x squared minus x cubed, around the y-axis. So if we did that, it would form this shape. And if we did our rectangle, like that rectangle what we've been drawing it, right, it would grow perpendicular. It grows from the axis of rotation perpendicularly. Until it covers that, we have to go through a hole first, and then we have the material, which means we would have two radii. There would be the little r here, and then there would be the big R that goes all the way out here, right? But there's a problem. The little r, we can use this curve to establish that, except that this r is in the x direction, which means you would have to solve this curve for x. And this is actually impossible to solve for x. There is no way that you can do that. We can't complete the square or other things like that. Not only that, but for the big R, right, the big R would also be established by that. So the little r and the big R both use the same curve, and they have to be solved for x, which is not possible. So since we can't really do that, we're going to use a different method. And the reason that we had to solve for x is because the rectangle was perpendicular to the axis of rotation. What if we decided to put the rectangle parallel to the axis of rotation? If we did that, then the dimensions there would be in the y direction, which means we wouldn't have to resolve this equation. And when we do that, that's called the shell method. And the difference is that the rectangle is placed parallel to the axis of rotation. All right, there's a couple things to know about this too. So in the disk method, the rectangle is perpendicular to the axis of rotation. We have our little phrase perpendicular to remember that. We write that, perpendicular. Perpendicular, I know it's corny, but it works. Right, we go parallel to the axis of rotation for the shell method. The little word we can remember for that is parashell. Shell is parashell, so parallel, disk is perpendicular. Okay. There's another thing to note too, though, that the rectangle starts on the axis of rotation. Because it's a radius. Now, the rectangle is not in the direction of the radius for the shell method. So actually, the rectangle here starts from the x or y axis. Right? So it doesn't grow from the axis of rotation, it grows from the x or the y axis instead. All right, so for us to use this, we're going to have to figure out what the dimensions of this object are and how they fill volume. So you can definitely see how the disk would fill volume, right? Because if you include a lot of disks here, it fills this space up here. What about the shell? Well, to make the cylinder for the disk method, we rotated the rectangle itself also around there. And we found that the volume was pi r squared dh, right? And we had a radius that established this here, right? What are the corresponding dimensions for the shell? Right? Well, we're going to do the same thing. We're going to imagine that we're rotating the shell also around the axis of rotation to form the volume. So if you rotate that one rectangle around there, it forms this object, which is not a disk. It's a little thin, kind of like a cylinder, if you want to think of it that way. Right? Well, it's not really a cylinder. It's more like a ring. that's been extruded upward. And then if you were then to take another rectangle down here and rotate that around, that would also make a little shell shape like that, right? And these things are like concentric rings, kind of like maybe when you were a kid, you had bath toys that had like cups that like were inside of each other like that. Like if you stack enough of those together, they do fill up the whole volume, right? So if you imagine they're kind of like nested cups, they fill up the volume that way, right? So what do we need to use as far as dimensions to deal with this object? Well, the first thing is that there's still a radius because we are rotating this rectangle around the axis of rotation. But now the radiuses always do grow from the axis of rotation. That radius is in this direction, but it's no longer in the same direction as the rectangle is growing. So we have to have a new letter for this, and that's actually going to be h for the height of the shell object. And then this little width here is no longer a change in height, it's a change in the radius. So it's in the same direction with the width as the radius. So the radius is in the same direction as the little differential change, which we call dr. Now, if you were to cut this object and open it up and lay it flat, it would open up into a box. And a box, the volume of a box is length times width times height. So the length of this box would be 2 pi r, the width of that box would be h, and then the height of the box would be dr. So, or you could reverse those. You could say 2 pi r, and then dr, and then the height of the box. So it's going to be this dimension. Now, why is that 2 pi r? Because if this radius is r, then this box's length is the distance around that we're going to open up, and that's just the circumference of that circle, which is 2 pi r. Then there's a height that we're labeling h, and then there's this little width here, dr, but that ends up being the thickness of the box. So it ends up being 2 pi r times h times dr. This is the volume per shell. Right, so that means we have a new formula. Right? We've got three formulas we've seen total. Right? Area is an integral from a to b of just height times d width. We've got disk method volume, that from the single integral is pi r squared dh. And now we've got a new one that we're calling shell, and it is an integral from a to b of 2 pi r h dr. Right? So a new formula to handle the volume per shell. Right? And the volume will be the sum of all these kind of nested cups to fill up the volume. All right, so now that we've got that, we can go ahead and solve this problem that was not solvable with disk method. First thing we'll do is, well, imagine we're rotating it around here. We'll go ahead and fill in the whole picture here. If we're rotating around the y-axis, that means there'll be another shape over here. That means we're kind of getting that shape like this, right? Got a bundt cake sort of. We're going to put the rectangle on here, but parashell. So it's going to be parallel to the axis of rotation. We're going to go somewhere in this bulk here, and we're going to grow not from the axis of rotation, but from the x or the y-axis. So we're going to just grow from the x-axis up here. Right? This is completely filled in, and that makes this a dx type. Right? And then we've got, if we imagine that we rotated that around, we would form the shell object. So if that rotated around, it would make a shell object that looks like this. And so I'll try to kind of sketch what it looks like. It looks like a cup, like a thick-walled cup. Right? It's got some dimensions here. This is the radius of that object, r, because if that radius grows from the axis of rotation, this little thing we call dr, and this dimension here we'll label h for the height. All right, so this boundary, which one does it establish? It's actually establishing the height. Okay? So that height is simply this y distance, which would just be this curve's y of 2x squared minus x cubed. So what is the r? Well, the r is not established by this height. It's just which rectangle we're on. So this is the part that's probably the most confusing. Right? When I'm working on this rectangle here, the r is this distance. When I'm working on this rectangle here, the r is this distance. When I'm working on this rectangle here, the r is this distance. So this r is simply the x for the current rectangle. Right, now here's how you can kind of keep that straight. If this is a dx type integral, because you've established the width, then this r is usually, as long as you're rotating around an x or y axis, it's just that same letter. The r is just that same letter r. So let's go ahead and build the formula for the volume. The volume is going to be, it is an integral from a to b of the volume for a shell element, which is 2 pi r h dr. Right? And so that's going to be 2 pi, okay, I'll skip that r for a second. The h is this 2x squared minus x cubed. This dr is this rectangle opening in the x direction, and this r is simply that same letter. So if that's an x, that's an x. Now, that will be a little more complicated later, but for now, think of it as always just being that same variable, possibly with an offset. And then we have an x here, so we have to bound this with x values. So this starts at x is 0, and we would have to know where this is back to 0. So what's unique about this point is that the y is 0 here and the y is 0 here. So if I took this 2x squared minus x and set that y equal to 0, I could factor out an x squared, and that would give me 2 minus x equals 0. So this goes to 0 when x is 0, and also 2, so this is x is 2. That means we're going to start and stop at 0 and 2. Okay, and that means that we can actually find this volume. It turns out to be 25.133. So here's an example of a problem that would be impossible to solve with this, but we can solve with this alternate method called the shell method. Okay, for the rest of the video, we're going to talk about a couple of other offshoots. Just like with the disk method, we can sometimes have to go through a hole first. Right? We don't have to do that in this case. In this particular example, right, disk method would have required that we had two integrals. That we would have to have a pi r squared df, in this case dy, minus a pi little r squared dy. But for this, switching to shell method, we only have a single integral. So sometimes this method results in less integrals, which makes it preferable. And even though problems on the AP Calc exam can always be solved with disk, they're okay with it if you use shell. Sometimes it's easier to use shell, so you're allowed to use shell on the AP exam if you would like. Okay, let's go ahead and look at another example. So, should we work this one? Let me look and see on my notes if we want to work this one. Yeah, I think just for purposes of illustration, let me just use this to illustrate, but we won't actually solve this one. So let's say we had two function curves. So we had a function curve y equals 1/2 x squared, and then we had that y equals 2x squared minus x cubed function curve. We wanted to rotate this around the y-axis, so like that. We would use, since we can't solve this, well, yeah, so we can't solve this one for x, we can't use disk, so we could use shell. We would put the rectangle on here, but because we're only taking the area between the two curves, we go through a hole first. Then that means that where before we had a big r and a little r, in the shell method we would have a big height and a little height. And that means you would have, actually let's use the 2 angle version. We would have 2 pi r big H dr from A to B, and then we would subtract out an integral of 2 pi r little h dr. Right? So it's the h that has a larger version and a smaller version. Same idea though. Okay, I think it's easier to see with some specific things, just emphasizing a few things, right? Disk method, rectangle is perpendicular, so perpendicular to the axis of rotation. Shell method is parashell, so parallel to the axis of rotation. The rectangle has to grow from the axis of rotation for disk method, has to grow from the x or y axis in the shell method. And then we have two different versions of the equation. The basic equation is pi r squared dh for this method, and it's 2 pi r h dr for shell method. All right, that means that we can just augment our procedure here. Always draw a sketch. Select a method, disk or shell, based on which one is easier to integrate. Sometimes you only have one integral versus two. Draw the rectangle. Determine the rectangle width, whether it's dx or dy, which establishes the variable of integration. Imagine rotating the rectangle to make the cylinder shape or the disk shape. Label things, so you're either labeling R or you're labeling H and R for shell, and then use the methods with the correct formula. Substitute everything in terms of the variable and evaluate if the problem doesn't state otherwise. All right, so we'll do more examples. A second example for okay, let's try this one. Use the method of cylindrical shells to find the volume. Now, if a problem were to state that you have to use a method, then you must use that method. That's true both on our tests and also for the AP exam. They don't typically, well, they never say that you have to use shell on the AP exam, but we might on our exams because we want you to know both methods. We're always going to start with a sketch. Let's do this without the calculator. Of course, we could use the calculator for this, but I think we want to emphasize that, something like well, half of the AP exam is no calculator, so let me make this a little smaller and give us some more room. And let's find this by hand. So if you're doing this by hand, we can treat this as an intersection. So if we have y equals negative x squared plus 6x plus or minus 6, and we have y equals x squared minus 6x plus 10. If we think of that as a system, we could say, let's see, x squared minus 6x plus 10 has to equal negative x squared plus 6x minus 6. If we get everything to the left side, that would be 2x squared minus 12x. And let's see, that's 10. If I subtract 6, that would be plus 16. Equals 0. I could factor a 2 out and give x squared minus 6x plus 8. And then that would factor into x, minus 2x minus 4, is that right? So that would be negative 6x, if that works, which means the intersections of x is 2 and x is 4. All right, and then I can find the matching y's by using either of these. So let's see. If I put a 2 in here, that would be 2 squared. So I'll use that space. 2 squared, y is 2 squared minus 6 times 2 plus 10. That's going to be 4 minus 12 plus 10. 4 minus 2 is 2. So that's going to be x is 2, y is 2 as an intersection point. And then if I put a 4 in here, that's going to be 4 squared. Let's see, minus 6 times 4 plus 10. So that's going to be 16 minus 24 plus 10, so that's going to be 26 minus 24 is 2, so that's going to be 4 comma 2. All right, so that gives me a lot of info for graphing. I will start by graphing the intersections. 2, 2, and 4, 2. And then one of these is an upward parabola and one's a downward parabola, so they must be doing that. Just from that, we can quickly see what's going on here. All right, so we're going to say rotating around the y-axis. So I'm not going to try to draw the sketch because it makes it or the 3D sketch here, but I will do what I would ask my students to do as the minimum sketch. So I would want them to do the 2D region and then draw the rectangle and label the rectangle. So if we're doing parallel or parashell shell method, we're going to put the rectangle parallel to the axis of rotation. That means it has to grow from coordinate axis, and that means we have two radiuses, 2 radii. We have a little r and we have a big R. Okay, the little r is a y distance, right? And it's established by this bottom curve, which is the upward opening parabola. So that little r is going to be x squared minus 6x plus 10. The big R is established by the downward opening parabola. So that y distance is negative x squared plus 6x minus 6. And that means I've got my two integral case. For parallel, the structure that we memorize is 2 pi r h dr minus an inner one for the little r. That's a big H, right? Oh, sorry, I should have labeled these H. Sorry for the confusion there. No, these are not R's, these are H's. Heights. The radius is this way. Because if I imagine rotating this, that radius is in that direction. So there's the downside of not sketching in 3D is it's harder to see why that's a radius. Let me just add a quick sketch line to show why that's true. If this is rotating around like that, that helps us see that this dimension is R, and therefore these dimensions are H. I apologize for that. All right, so then this is going to be 2 pi r little h dr. This width is in the x direction. So we're going to have an integral 2 pi. Skip the r for a second. This h, big H, is negative x squared plus 6x minus 6 dx. And then this r is simply the x for the current rectangle we're on. So that is an x. Minus integral 2 pi. We'll skip the r for a second. The little h is x squared minus 6x plus 10 dx, and that's x. And then we have to cover this in x. So we're going to go from this x to this x, so that's from x is 2 to x is 4 for both these integrals. This is the integral setup. And if you do math 9, you end up getting 50.265. Okay. So a little bit more work, I think, for shell than disk, but it's a really good way to do it. This didn't really save us anything. Disk or shell, both of these would have required. Actually, this would be more difficult to do with disk, because if you did try to do this with disk, you've got this shape here. Disk would require that we put the rectangle this way, and that means we'd have the same function for the ceiling and the floor, and over here. So we'd have to split it into two integrals, right? I think that would be trickier. We could still do it with this, but volume is definitely better for this one. All right, let's do another example here. Some more space. And we'll try it. So let's sketch first. Again, I'm going to show, because I know everybody can plug things in the calculator, I'm going to show examples of how to do this without the calculator. Go ahead and pause it. The video, try it, and unpause to see if you can get this right. So we have, so x is the square root of y, x equals 0. Let's just intersect those two. The square root of y would equal 0 when y is 0. Actually, I think I can just sketch this without taking an intersection. Maybe I should do this instead for this problem. X's square root of y is the same as x squared is equal to y, right? And I know how to sketch that easily. So x squared is equal to y is this. The fact that it's written this way, x is the square root of y, means that it's prohibiting negative x's. So it's only the positive x part of y equals x squared. So 1, 1, 2, 4. This would be something like that. This is x is the square root of y. X is 0 is the y-axis, and y is equals 1 is this. Okay, so it's actually this region here. All right, then we're rotating around the x-axis. Okay, so the x-axis is axis of rotation. That means that I'll go ahead and draw this in. This is the shape. We're going to use shell method. That means that we're going to put a rectangle parallel to the axis of rotation starting from a coordinate axis. So that's going to go this way. It's completely filled in with material. So it is a dy type width, and this is a dimension, and this is a dimension. This is the radius here, which makes this dimension the height. And then we've got, let's see, for that height, it's established, it's an x distance established by this boundary curve, so that it's simply the square root of y. Now we can say single integral, here's the pattern, 2 pi r h dr. So in this case, it's 2 pi, let's skip r for a second, h is the square root of y, dr is a little change in the y direction, and this r is simply the y coordinate for the particular rectangle we're on, so it is y. And then we have to cover this in y, so that'd be from y equals 0 to 1. This is the setup, it wasn't too bad. And it ends up being 2.513. Boys round to 3 meters. Okay, how many more do we have? 1, 2, 3 more. Yeah, let me go ahead and split those off to another video. If you're watching, well, we haven't seen an offset axis case, which we're going to see in the next case. So let me do one more. Yeah, let's put all in one video. So you can stop whenever you get to the point where you feel comfortable. But we definitely need to see this next example, because this covers rotating around something other than one of the coordinate axes. All right, so let's do this. It's going to involve an offset, but there is something tricky to know about it for shell method specifically. We've got to sketch this region. So this one we can sketch pretty well. Let's sketch it this way. 1, 2, 3, 4. I'm just writing that the axis of rotation here is actually axis 4. So we're rotating around that. So I need this to be pretty far out here. X and Y. Okay, so 1, 1, 2 would be 4. I won't make this to scale. Let's make this. We're gonna go from x's 1 to x's 2. So 1, 2, 3, 4. This will be fine. This is y equals square root of x. Y equals 0. X equals 1. X equals 2. Those are vertical lines. So this is the region. Okay. But we're rotating it around x is 4. So if I wanted to do the rotation, there would be another chunk over here like this. That's looking like this. So this is the shape we're doing here. Okay. So we're going to use the shell method, which means parashell. We put the rectangle parallel to the axis of rotation. So that means up and down. So in this bulk here, I'm going to put a rectangle. This is a dx type because it's looking in the x direction. Right. The radius is this. It's from the axis of rotation to the object. So that's the r. The h is in this direction, and it's completely filled in, so there's only one h. And that h is a y distance. So it's being established by this boundary, so it is the x squared using this letter. Okay, now the trick is we have to deal with this r. Okay, so what is this r? Well, first of all, it's in the same, if I put the expression here, the pattern 2 pi r h dr, it's going to be in the same direction as dr, and it's this, right, which normally we would say that that is just equal to the x for the rectangle we're on, and that's this distance. This distance here is the current x for the rectangle we're on, right? But this r is this distance, not this distance. So there's another distance involved, and that's this distance. This distance is 4, right? Because we're rotating about the x-axis, or the axis x equals 4. So you have to do a little algebra here. X plus the r has to add up to 4. X plus the r must be 4. Therefore, r has to be 4 take away x. So this r is this distance 4 minus the x for the current rectangle we're on. So whenever you're rotating around an axis that's not an x or a y axis, this r is a little more complicated than simply the copy of this letter. So in here, this is 2 pi. This r is 4 minus x. and this h is the height that's established by the curve, which is x squared, and then this is dx. And we're integrating, but we're only integrating from x's 1 to x's 2. That's the only rectangles we want. So this is the correct setup. All right, so this r, it's either just x, or it is either like a number minus x, or it is x minus a number. It's never more complicated than that. But when you're rotating around an axis other than the x or y axis, it's more complicated. So this is the correct setup. And Math 9 says this is 35.081. You might, on your homework, practice integrating a couple of these by hand. These are not hard to integrate. Often they're polynomials. Okay, number 5 says set up but do not evaluate an integral for this. All right, so we will go ahead and try that. Smaller. 2 more examples to wrap this up. All right, let's sketch the situation. All right, so we've got, it's crazy, x equals the square root of sine of y. You know, I think for this one, I'm going to actually have to graph this probably. Well, maybe not. No, maybe not. How the square root makes it tricky. All right, so how do we deal with this? X equals sine of y. Well, x equals square root of sine of y. We could graph it with a calculator, except that the calculator has to solve for y. So if you had a calculator on this part of the test, you could graph it this way by plugging in, let's reverse the x and the y. Okay? So we could say y is the square root of the sine of the variable px. Now if we did that and graphed it, do 9, we would get something that looks like this, except that the x and the y axes are reversed. So that means you would have to, for sketching it, you'd have to say, all right, this has to look like this. Then. It would, see, that other graph looked like this, right? So this one is going to look like this. Okay, so here's a graph of what's going on. You can sketch it, and you can, and then it says only 0 to pi, so that means one copy of this. So let me actually sketch it a little bit more nicely. Okay. So just one chunk of that would look like this. This would be 0 and this would be pi. Right? Because if you put pi in there, sine of pi is 0. So x is 0 when y is 0, and x is 0 when y is pi. So this is what we've got here. And then we're taking the area from the other axis is x is 0, which is the y-axis. So it is this region, but we're rotating it around the line y equals 4, right? So where is that? Well, pi is about 3.14, so y is 4 would be somewhere up here. We're rotating around that, which means that there's another chunk up here, and we're rotating this way. All right. So yeah, pretty tricky, because now we're going to put shell method, growing not from the axis of rotation, but from one of the coordinate axis to cover the material. This is nice. We only have one integral here. It's a dy type. Okay, and that means that the radius of the object is going to be from the axis of rotation to that rectangle. And then the other dimension, we're going to label height. So this is the height. The height is an x coordinate. It's an x distance established by this boundary. So it is the square root of sine of y. Right? And then we can build our integral from a to b, 2 pi r h dr. So this is going to be 2 pi. I'll leave the radius for a second. The height is the square root of sine of y, and this is a dy type. Now, this r is not simply the y. This is the y for the current rectangle we're on, but this distance is 4, so this r is 4 take away the y. So 4 take away the y, and then we're integrating from a y of 0 to y of pi. This would be the setup to get the correct answer there. And it said do not evaluate, so we'll leave it like that. Okay. Maybe this would be a good one to illustrate that if you have something that you're trying to graph and it's really difficult, you can reverse swap the x's and y's. If I just swapped x and y, what would happen? This graph would change to be this graph. We would be rotating around this line, but it doesn't really matter if you change the x's and y's around, as long as you do that throughout the entire problem. Your teacher may or may not allow this, so you should ask. But for my students, I allow this if they tell me that I am swapping x and y, swap x and y, and then they rewrite the problem. So this would be y equals the square root of sine of x. This would be x going from 0 to pi. This would be the line y equals 0, and it would be going about the line x equals 4. So if you write that, it makes it easier to graph, so that you can just plug that directly in your calculator. But you would get almost the same setup. The only difference is you would be using the letter y, or x instead. So it's perfectly fine to swap them if your teacher allows it. I require mine to write that that's what they're doing first before they do it. But changing the letters does not change the value of the volume, so that's legal. And I believe you should be able to do that on the AP exam too. Just always indicate what you're doing. Okay, last example. Use a graph to estimate the x-coordinates of the point at the intersection of the curves. Use this information to estimate the volume. Okay. So this one we're going to do by hand. And we'll start with a sketch with intersection. So if we think of this as y equals x to the fourth and y equals 3x minus x cubed as a system, could we set those equal? Yeah, we could say x to the fourth equals 3x minus x cubed, and x to the fourth plus x cubed minus 3x equals 0. Factor an x out and we get x cubed plus x squared minus 3 equals 0. Wow. There's no real good way to solve that. So I think in this case, we're just going to resort to a calculator. I think we have to in this case. We wouldn't ever have anything that complicated or we didn't allow a calculator. So we're going to do this with the calculator. I'll just go ahead and plug these in. Y equals x to the fourth. And then for the other 3x minus x cubed. We'll graph near the origin, zoom 6. There's the x to the fourth curve. Okay, there's a lot going on right in here, so I'm going to change my window to only go from -2 to 2, and we'll see if I can see everything that's going on down there. That far out. You see what's happening? Okay, there's the y equals x to the fourth. Here's the other one. Okay, yeah, so that's what's going on. There is one enclosed area, which is this area in here. So that gives me enough to sketch what's going on here. Let's go ahead while we're here and figure out where this intersection is. This appears to be 0, 0, and that would be true because I've put a 0 in here. I would get y is 0 and 0, 0. So 0, 0 makes both of these true, but what is this intersection point? Let's do that while we're here. We can go up here. First curve, second curve, yes. Okay, yeah, it's not at an integer boundary. So 1.174. I'm going to go a little extra here because I want the final answer to be correct. So 1.17456 maybe. 1.17456. So let me make a sketch now. looked like we had, let's see, a curve that kind of went like this, and then another curve that sort of went like this. This was the area, and this point was at 1.1746. I'll go at least one extra decimal point, 1.9033 at the intersection. And this is the 0.00. Yeah, we would have had, that would not have been factorable. We would have to use a calculator for this. Okay, we're rotating about the y-axis, so that means this is the axis of rotation. We can put the rectangle on here now. If we're doing parallel or shell method, parallel, we're going parallel to this axis of rotation. We're going to draw a rectangle like this. Goes through a hole before it gets to material. This is a dx type. That means that we have two heights. There's a little height, h. There's a big height, big H. And there's a radius, r. Right? The little height is established by the bottom curve, which is the x to the fourth curve, right? Yeah. The little height is this y, which is x to the fourth. And the big height is the other curve, y, which is 3x minus x cubed. The volume will be two integrals, a to b 2 pi r h dr minus, this is a big H for this one, 2 pi little r little h dr. So 2 pi, we'll skip r for a second. The big H is 3x minus x cubed dx. 2 pi, skip that, x to the fourth, we get h dx. And then in this case, this r is simply the x that we're on for that particular rectangle. So that is just x, we rotate around an axis. And then we have to integrate this across x's. So this is going to be from 0 to 1.1746. 1.1746. And the correct answer is 4.622. All right. So a little trickier than disk, but it allows you to do some integrals more simply than disk, and it allows us to do some integrals where disk does not work. But AP exam, every one can be solved with the disk method. Shell is not required on the AP exam. All right, that should be the last example.